the screen should be visible.
Yeah.
So today, basically, I'll be talking about proof techniques and, some of the logical errors we make while writing proofs. So I guess I should start off by, defining mathematical statements or something. So first of all, a mathematical statement is something which is like either true or false. So let's say I have the statement, I am a cat, right? So this statement could either be true or false. So like you could say this is a mathematical statement P, right? And usually in mathematics proofs, we use the imply statement, right? Which just means that like if you have P implies Q, this is the same thing as if P is true, then Q is true. So I could write something like if P is I am a cat and you know uh, Q is I am an animal, right? I could say P implies Q because if P then Q. If I'm a cat, I'm also an animal. Also, I wouldn't be able to see your chat, so if you're messaging or something, please speak up. Anyways, so yeah. So sometimes in problems, we'll see stuff like uh, show that P is true if and only if. Sometimes shorthanded as if with two F's because we are lazy. Q is true. So in this case, there's actually one statement which we have to show, like we have to show two statements. So we have to show first P implies Q and then Q implies P, right? So this is the sort of thing you might see on an Olympiad problem, like you want to show this is true if and only if something else is true. So also as an example, just to make sure we know things are right. So is this statement true? Anyone? Hello? Okay, so this is just like saying x is 1 or 2, right?
It is true, no?
Yeah, this is true. This statement is true. But like obviously we won't be saying that 2 is a solution to this equation, right? So whenever I ask you to, let's say, solve an equation, solve x minus 1 equals to 0, we actually need to show two directions. This is a two-direction problem. So we need to show x minus 1 is 0 is actually equivalent to x equals 1. So there are usually a lot of if and only if statements hidden, which we'll actually see later on. So anyway, now I'll be moving on to proof techniques. So probably the most common proof technique used in Olympiad problem is the technique of contradiction, which you probably have seen a bunch of times already, but I'll still say how it works. So let's say you want to show something like P implies Q, right? So what you do in method of contradiction is you assume that P is true and Q is false and show that this is impossible. So if this is true, like if you manage to show this, then Q could not have been false, so it must have been true, which means that P implies Q is true. So as an example, okay, let's start with an easy example. So you must have heard of the pigeonhole principle, right? If I have n plus 1 pigeons in n holes, then there is a hole with at least 2 pigeons in it. So would someone like to, give a proof using contradiction? Okay, so yeah. So well, so
Like,
what we do.
suppose not, then
Hmm.
each has at most one pigeon, which means there can be at most n pigeons.
Yeah, exactly. So if this is false, like, so what we're trying to show right now is if n plus 1 pigeons and n holes implies there is a hole with at least 2 pigeons. So as you can see, like in the contradiction, you want to assume that this is false. So you want to assume this is false. So that means that you need to assume that for all holes, there is at most one pigeon. So there is at most one pigeon here, at most one pigeon here, and so on. But then since there are only n holes, we could have at most n pigeons. But then we have n plus 1 pigeons. So that's a contradiction. Right. So yeah, you can show things this way too. Now, another way of phrasing the same thing is using the contrapositive of the statement. Is the proof clear, by the way? If it's not, you can ask me, I'll repeat it. Okay, I'll assume it's clear then. Yeah, so contrapositive of a statement. So if a statement P implies Q, this is actually the same as the, negation of Q implies the negation of P. Now, negation of Q is just if Q is true, then negation Q, okay, I should say this properly. So if Q is true, then negation Q is false. And like it flips basically. If Q is false, then negative Q is true. Does anyone have a question? Okay. Yeah. So it just flips this. So this is actually the same thing as contradictions. It's like if you have negative Q is true, then like this what this statement says is that if negative Q is true, then negative uh, P is true, which is the same thing as saying that if Q is false, then P is false. But we already know this because like by contradiction, if P was true, then Q would be true because we know this, right? But then we know Q is false, so that can't be possible. So yeah, so this is the contrapositive of this statement. They actually mean the same thing, but this is just a different way of like representing it. So we could also prove like PHP based on that. So what I'll show now is that okay, wait. Yeah, sure. So what I'll show now is that like we see the contrapositive in the contradiction statement only. Like if we assume the contradiction, so this for all holes there is at most one pigeon, and then we showed that there are at most n pigeons, and that happens to be the opposite of this statement, where if you replace this statement with a general statement that if you have greater than n pigeons, right? And so then this becomes the contrapositive itself. Um, any questions here? Okay. So, okay, I guess we can start. We can do another problem based on contradiction. Show that if x square is even, then so is x. Again, don't use number theory or whatever. We'll just use contradiction. Yeah.
Can I try?
Yeah.
Okay, so let's assume that x square is odd.
No, you can't do that. You have to assume that this is odd because like when we are looking at the statement of P implies Q, in the contradiction, we want to assume that this is false. So if let's say by chance you showed that x square odd implies x odd, you have shown nothing when x is even, right?
Okay, so let's
So
assume x is odd.
yeah, so you assume x is odd, fine.
Then if you multiply an odd by an odd, then it is an odd. We
Yeah,
can do it by like 2n plus 1, where n
yes,
belongs
that
to
works.
any integer.
Yeah, this is odd basically. Yeah, and so yes, you're right. So in that
So we
case,
are
x squared yeah, continue.
getting x square to be odd, which concludes that x should be even if x square is even.
Yes, exactly. So in some sense, this is the contrapositive of this statement, right? Because we have the opposite of this statement and the opposite of this statement. Because contrapositive is just, contradiction in the same way. Okay, so a slightly harder problem, I guess. So, okay, a given n friends in a party, it's a very popular question. Show that um, two people have same number of friends. Friendship is mutual and you can try this problem for 5 minutes if you haven't seen it. I'll tell the solution in like 2 minutes.
I have a doubt in this question.
Yeah.
If there are odd number of friends, suppose, then how can this be true?
Odd number of friends as in for every person.
Yeah, like see, there are n friends, right? What if n was an odd number? Then
Oh,
how
and
can
friends. Okay, my bad. This is just 1 second. This is just n people, and like some people are friends, right?
okay.
So they just need to have same number of friends. So as an example, let's have person A, B, C, and D. And let's say A is friends with B and B is friends with C. Let's have this and this. So, okay, I join two things with a line if like they're friends, right? So A and D are friends, B and D are friends, A and B are friends, B and C are friends. So in this case, this has, 3 friends, 2 friends, 2 friends, and 1 friend. So you can see A and D have the same number of friends. Show that this is always true, is what you want to show.
Can I try?
Yeah.
Okay, so every person in the party can have from 1 to n minus 1 friends, which means
Uh,
that there are n minus 1 possibilities, and we are like dividing them among n people,
yeah.
or assigning them to n people. And this
Yeah,
is
but
similar to the pigeon and
yeah,
hog
that's true.
problem.
But you could also have 0 friends. Like you could also have, C nots friends with anyone.
Mm.
Like in that case, the pigeonhole argument doesn't work because well, you have n things and then n, people. So how would you fix this?
Zero and n minus one can't be together. Then n minus one means he should be friends with everyone.
Yeah, yeah, exactly. So if I have, a person friends with everyone and a person friends with no one, they can't exist together because, well, will they be friends or not? If they were friends, this guy doesn't have 0 friends, and if they are not friends, this guy doesn't have n minus 1 friends. So you either have, you know, 0, 1, 2, n minus 2, the possible values, or 1 to n minus 1 possible values. In both cases, by the same argument, you can't, you know, it's a contradiction basically. Okay, I guess we'll do one last one and then. Actually, it's fine. Yeah. Uh, so yeah, that was the first technique, the proof technique which we use. And the second one, which is a more of a proof technique, I guess, is induction. All right. So let's start with what induction actually is. So let's say I have a statement P, which depends on a variable n, right? So P of 1 could be true, P of 2 could be false, and I don't know, P of 3 could be true, and so on. So like you have a bunch of statements, infinitely many statements actually. And you have the following. You know that P of 1 is true. And you have that for whatever k I choose, like which is a natural number, P of k implies P of k plus 1. Right, so if P of k is true, that implies P of k plus 1 is true. Then by the principle of induction, we have that P of n is always true for all n. It should be intuitively pretty clear. So, I have P of 1 true. And well, by this thing, I know that if P of 1 is true, then so is P of 2. So I know that P of 2 is true. But then similarly, since I know P of 2 is true, I know P of 3 is true. And I can just keep going on like this. And so I'll have every statement is true for everything. So although it's a pretty obvious statement, like really powerful in its applications. So we'll be seeing some of those. So, okay. You use this in pretty much like uses in all three: algebra, combinatorics, and number theory. So let's start with an algebra example. It is a pretty simple one. Yeah. So show this is true for all n in natural numbers using induction. Yeah. So, okay, so one important thing to note is that even though this is the main part, you also need to establish this is true. Or else you could come up with quite wrong things, which I'll show probably. But yeah, so don't forget the base case. And sometimes there might even be more than one base case you need to check. So like, be careful with your base cases.
Can I try?
Yeah.
Okay, so let's put the value of n to be 1 and 2. Let's test for 1 and 2.
All right.
When n is 1, we have 1 plus 2 on the left hand side, which is 3. And for the right hand side, we have 4 minus 1, which is also 3.
Yeah.
For n equals to 2, we have 1 plus 2 plus 4, which is 7. And right hand side is 8 minus 1, which is also 7.
Yes, but do you really need multiple base cases here?
No, we don't need multiple cases, but let's just
Sure.
try to test.
Sure, sure, sure.
Okay, now let's assume for n.
Right.
So I mean for assume for n equals to k,
Right, exactly.
that 1 plus 2 plus up until 2 raised to the power k equals to 2 raised to the power k minus 2 raised to the power k plus 1 minus.
Right.
Now we have to prove for n equals to k plus 1. So for the left hand side, we have okay, wait. We have to prove 1 plus 2 plus up until 2 raised to the power k plus 1
Right.
is equals to 2 raised to the power k plus 2 minus 1. We have to
Yes.
prove this.
Yes.
Okay, so let's start with the left hand side. Elaborate 1 plus 2 plus up until 2 raised to the power k plus 2 raised to the power k plus 1.
Okay.
We have assumed that 1 plus up until 2 raised to the power k is equals to 2 raised to the power k plus 1 minus 1.
Right.
It's 2 raised to the power k.
What?
One number is 2 raised to the power k. You have written
Where?
2 raised to the in the last second step.
Here.
Oh, wait.
No, this time is just 2 to the power of k plus 1 minus 1, right? From what we assume.
Yeah.
And yeah,
Okay.
you get that.
So basically we have 2 into 2 raised to the power k plus 2 minus 1.
Yeah. So, and this is what we wanted to show. So like, we have shown induction hypothesis.
And by the induction hypothesis, this is true for every n belongs to natural numbers.
Yeah. Yeah. So, as we can see, so the first thing we did was check that P of 1 is true. So, base case 1. This is actually not needed, but you can write it down anyways. There's no harm there. But, and then what we did is we assumed it for n equals k and showed that if it is true for n equals k, so if P of k is true, then P of k plus 1 is true. Right. So, okay, yeah. So this is how induction works. Does anyone have any doubt?
Can we do something different to show that induction indeed works?
As in,
Like,
different.
question is, prove that sum of first natural number is equals to not n into n plus 1 divided by 2, but n plus 1 divided by 2.
Mm,
Okay, so my question is 1 plus 2 plus up until n is equals to n plus 1 divided by 2. Well, this is not true,
yeah.
but let's just do it so that we know that induction is true, like induction works.
Okay.
Let's assume for n equals to 1.
Yeah. N equals to 1, it will work.
Yeah, it works for n equals to 1, but let's assume for k now.
Yeah.
And prove for k plus 1.
So like in this case, it won't give the correct thing.
Yeah.
Right? Because
So that was the reason to show that induction works.
okay.
It actually works, induction. Like,
Yeah, it is true. Right. So like, yeah, if you try to do this, you would get, if you try to do the same thing, you would get k plus 1 by 2 plus k plus 1, which does not give the correct thing. So this is false. Like this is false.
yeah, this does not give k plus 2 divided by 2.
Yeah. Yeah. All right. Any other questions? Okay, we'll do, I guess, another algebraic example. So show that for all n at least 4, 2 to the n is less than n factorial, where n factorial is 1 times 2 times so on till n. So does everyone see why intuitively this should be true? Just think about it for a bit.
Can I do it again?
Sure. Although I guess let's wait for a minute so that everyone tries it at least.
And can you explain the last question of contradiction method? I didn't get that question.
The friends one.
Yeah.
Right. So yeah, did you not understand the question or the solution?
I understand the question, but I didn't get the solution.
Right. So okay. So let's look at each person. Let's say A. For now, let's just assume there are 4 people, right? So yeah. So what is the possible number of friends he could have? He could have 0 friends, 1 friend, 2 friends, 3, or 3 friends. He cannot have 4 friends, right? Because there are only 4 people. Agreed?
Yeah.
Yeah. So there are only 4 possible values. And if we assume that each person has a different value, like of a different number of friends, because we are assuming contradiction, right? That like
Yeah.
there are no 2 people having same number of friends.
Everyone has this different number of friends.
Yes, exactly. So since there are 4 possible values and 4 people, and each one has a different value, someone must get a 0 and someone must get a 3, right?
Yeah.
So let's say B got a 0 and A got a 3. Can they be friends?
Yeah, they can be friends. Like there are 4 people, so A can be friend
No,
with.
but B has 0 friends, right? So they can't be friends.
Oh,
But can they not be friends too? Because A
that
is friends with everyone. Because A has 3 friends, it is friends with everyone.
so that's a contradiction.
Yes, exactly. So that's a contradiction. Yes.
Okay. Okay. Thank you.
Yeah. Yeah. Anyway, so to this problem, yeah, you can see the solution on the page. Okay, so you wanted to say the solution too?
Yeah.
Yeah.
Test for 4 n equals to 4. We have 16, which is less than 24.
Yes.
Let's assume for k, 2 raised to the power k is less than k factorial.
Mhm.
We have to prove that 2 raised to the power k plus 1 factorial, or I mean 2 raised to the power k plus 1 is less than k plus 1 factorial.
Yes.
And let's elaborate the right hand side. Start from the right hand side. We
Okay.
have 1 into up till k into k plus 1.
Yes.
And for 1 into k, we have 1 up till k, we have 2 raised to the power k.
Yeah, B weight is greater than 2 raised to the power of k.
Yeah.
Hmm.
But we already know that k is not less than 4. So it has to be greater than equal to 4, which means that we can substitute for k to be 1.
Yeah, so basically you're just saying k is greater than or equal to 1. So
Yeah.
I can just write 2 to the
2
k
raised to the power k into
times
2.
1 plus 2. Let's just say. Since k is at least 1, this thing is at
Like
least 2.
I think k cannot be 1. It has to be greater than equal to 4.
Yeah, but since we are assuming this bound already, so we can just say this directly. Because this is what we want, right? So
Okay.
yeah. Yes,
That's
that works.
that's the proof.
So why do you think we needed n at least 4? Like, because here we just use k greater than or equal to 1, right? Why can't we just say for all n greater than or equal to 1?
It does not work for 1, 2, 3.
Yes, exactly. So we also needed the base case to hold, otherwise we can't move forward. Even though this is working, the induction hypothesis is working, but till the base case doesn't satisfy, we can't, go forward. So yeah, so base case is pretty important. Anyway, now let's do a combo problem. So show that if I were 2 to the n times 2 to, okay, let's say 2 to the 100 times 2 to the 100 board, and I remove a, cell from it, right? Show that I can tile it using terminals. Terminals are figures of this shape. Right, so okay, let's just do it for 2 into 2 board. Show that whatever way I remove it, I can tile the remaining shape by terminal, is what you want to show. And tiling is just placing terminals such that no two intersect, and like these are on the cells of the board.
What are trominos?
Terminals are 3 cells placed together like this. So okay, I guess I'm for 4 times 4. Let's remove this. Okay, I will tile it. And yeah, you get my point. So show that you can do that even for 2 to the power of 100 times 2 to the power of 100 board. Okay, then has anyone got any idea? Mhm. No, you can get whatever you want. So what have you tried?
Can I try?
Yeah.
Okay, so we saw that it works for 2 by 2.
Yeah. So for 2 by
And
2 by symmetry, whatever you do, you
yes,
can just do it.
yes. So when we move or multiply by 2 or 4 in this case, so
Right.
we get 4 by 4, or the next round we get 8 by 8 or something like that.
Yeah.
We're basically multiplying the size by 4.
Yes. So
Yes.
you're just
And
splitting the new grid into 4 parts. So
yes,
yes.
okay. Now, one of those squares can be done. We've shown that in the previous step.
One of the squares has the
So we can do the upright triangle or square. We've shown that in the
Yeah.
previous step.
Yes,
And we
exactly.
can place this shape on the corner of it and like remove one square from each of the other by this
Correct.
shape.
So we can remove this one, this one, this one.
And then we can do those because we've proved that before.
Yeah, exactly. So basically, once again, we use induction, and base case of 2 times 2 is pretty easy by symmetry. And so what we'll show is that if for n equals k, so if you have 2 times 2 to the power of k times 2 to the power of k, if this is true, we will show it for 2 to the power of k plus 1 times 2 to the power of k plus 1. So what I'll do now is I'll take the 2 to the power of k plus 1 grid and split it into 4 parts, each of size 2 to the power of k times 2 to the power of k. And okay, we know that there will be one part where I have removed a square. So by induction hypothesis, I can tile this by a terminus in some way, however that is. So this part is dealt with. So now the problem is that we want to tile these 3 things too. So what we do for that is we take a terminus here, right? And we practically have just removed these squares. And now I'll just tile this other parts using terminals. And in this way, we can tile the entire board using terminals. Is it clear?
Yes.
Yeah. Okay. Let's do another combo problem. Yeah.
I got a kind of different solution, but I don't know whether it's correct. Like, can I
Sure.
see?
Oh, yes.
Yeah, so you said there are 2 to the power of 100. The board is like 2 to the power of 100 into 2 to the power of 100, like, right?
Yeah.
So yeah, you see the total number of tiles will be 2 to the power of 200, right?
Yeah.
Yeah, 2 to the power of 200. So yeah, the question says you have to just remove one tile from that. So if you see 2 to the power of any even multiple, minus 1 will give you a multiple of 3. So however, that
Yeah.
shape itself is a multiple of 3, right?
Yes.
So does that
But
prove?
that's not necessarily true, right? Let's say I give you this shape. Can you tell this isn't Trominos?
No.
Yes. So even if you have that, 3 divides the number of tiles in whatever, you can't necessarily tile it isn't Trominos. But if you in fact had that 3 does not divide it, then you can definitely say that, you can't tile it.
Yeah.
But if you know 3 divides that thing, you don't really know whether you can tile it or not.
Yeah.
Yeah.
So this approach does not work actually. Like there,
No.
like I got this actually. Like we can arrange in this type of shape also. But yeah, I thought is there any forward approach? So there is nothing, right?
No.
Okay. Thank you.
Okay, so let's do yet another combo problem. So let's have n lines and no 3 are concurrent or parallel, and like no 2 are parallel. And if I'll give an example. So if I have 3 lines, right, they form these regions, right? So you have in region 1, 2, 3, 4, 5, 6, and 7. So show that you can color these regions red and this is blue, red and blue, such that the adjacent ones have different color. I'll repeat just a second. Yeah. So you want to show that you can color regions in red and blue such that adjacent ones are different colored. There's an example. Of such a coloring.
Sorry, I don't understand the problem. Could you explain it?
So yeah. So this is the case for n equals 3. So I'll take 3 lines, right? And if okay, let's just take 2 lines. So you see that it splits the plane into these regions, right?
Yes.
So you consider all these regions and you give them a color. So this is, let's say blue color. This is red color. So is this, and so on. And you want it such that if I have two regions which are separated by a line, I want them to have different color. So for example, this one and this region, region number 1 and 2, they share an edge basically. So in that case, they must have a different color. So I color one red, then 2 must be blue. And you want to show that such a coloring is possible.
All right.
I'll see the solution in a minute. Any ideas?
Yes, can I try?
Yeah,
But I'm not sure.
sure.
Uh, I think we can prove that for any line we choose,
Mhm.
at any point in that line, the two colors should be different. So we can do that.
Yes. Yes, this
It's
is, yeah.
equivalent to showing that. Okay, so we can first start with one line and coloring two opposite colors in the two
Yeah.
sides. And then by adding one line each time, we can flip the colors on one side of the line.
So you're saying
And
that
that
this
will,
was red before, and now this is blue.
yes,
And since this was blue before, this is red.
yes,
Yes.
yes.
Yes,
So
this
I think
works.
this will result in, yes,
Except when you're writing it, as a proof, you'll want to go it in the backwards direction. So like if you're using induction, right? So you want to show that like, okay, so you take n lines initially, and you sort of take the answer for the n minus 1 lines, right? So you the coloring rather, and then add that line, where adding that line involves flipping on one side. So when you're writing the proof, you're instead of going, I take one line and then keep adding things, you could say that's an equally valid proof, but it's usually better to write it in an inductive way. So yeah, but yes, this works. So the proof is basically you take take n minus 1 lines among those, and by induction, already you know that you can color these in such a way, and whatever coloring you have, okay. Whatever coloring you have, is- yeah. And if I add this one line, I will just flip these colors, right? And we already, the regions near this line would never contradict the assumption because we are flipping this, right? And they were of the initial, they were of the same color initially. So that's not a problem. And the already existing ones are not disturbed, as you can check, because on one side it's just the same, and then on the other side everything has been flipped. So it still satisfies the condition. So we can see that, you know, this still works. So this coloring works. Any question? Oh, it's in the chart. One second. Yeah. Okay, so I'll move on to the next question. Also, yeah, you can, you know, send it to me on Discord if you want. Yeah, so that was, you know, going from K to K plus 1 is the standard induction. But you also have a thing called strong induction, where not only do you assume the statement is true for K, you also assume it to hold true for P of 1, P of 2, and so on till P of K. So in that way, you know, you get a lot more information than just with K. And obviously, you also need to establish the base case. You also need to show P of 1 is true. And once again, this works the same way as like normal induction, because P of 1 is true, that implies P of 2 is true. Since, you know, both P of 1 and P of 2 are true, we can keep going forward like this. So, yeah. So once again, since this gives you, you know, more information like directly, like it gives strictly more information than normal induction, you can do most of, you know, using this. So, yeah, as an example, let's say we wanted to show that, yeah, okay. So this is the problem in between. Show that like base 2 representation is unique. So for example, you know, given a number n, I need to, you know, represent it as a sum of powers of 2. So 2 to the power of 0 plus 2 to the power of 4 plus 2 to the power of 5, whatever this is. And I should show that this is unique. Okay, so I'll just do this one unless you have any ideas. Okay. So basically, okay, we are familiar with this base system and all that. So we know that you can represent it like this. What is this? 1 0 0. Yeah, this is the whatever the n I'm talking about. So well, what we need to so we are trying to induct, right? Because we want to show uniqueness, and like if we establish uniqueness for the previous values, we also want to establish it for the next value. So going from n-1 to n seems weird because while adding the +1, there could be carryovers and whatnot. I think it is still possible, but it is a bit annoying. So what we'll do is we'll induct on the number of digits. Right. So so I need to remove the uh, okay, I just realized I wrote this wrong. 1 second. Uh, yes. Yeah, so I want to delete the largest power of 2 and then use this remaining part. So what I'll do is I'll consider the d such that 2 to the power of d is at most n, which is less than 2 to the power of d plus 1. So I'm just picking the largest power of 2, which is at most the number itself. Right. And now I'll subtract this with 2 to the power of d. So, okay, so we are using strong induction here. So obviously 0 is, okay, obviously 1 is representable, right? Just pick 2 to the power of 0. So let's say everything until, n-1 is already shown. So p of 1 is shown till n-1. And now I want to show p of n using this, right? So yeah, so now I know that this number is less than 2 to the power of d, which is obviously less than n. So I know that this number has a unique representation uh, as sum of powers of 2. But obviously, if I have equal to that a plus 2 to the power of b and whatnot, then a must be less than d, because we already know that this sum, where is this? Yeah, we already know that n minus 2 to the power of d is less than 2 to the power of d. So I can't have 2 to the power of d here. So this number, let's call it m, right? So we know that m is uniquely representable as sum of powers of 2 with the largest power less than d. So now to the representation of n, I can just add 2 to the d plus whatever the powers of 2 I have for m. And here we are using the strong induction hypothesis because uh, it's just a number less than n. We don't know if it's a previous number or not. So since we know that all of them are true, this p of n minus 2 to the power of d is also true. And so we can use this hypothesis. And so yeah, since each number has a unique maximum power of 2 at most state, this representation is also unique. And so we are done. Was this clear or should I repeat?
Can you repeat?
Yeah. So, okay, so what we are doing now is, so this is the question. Yeah, base 2 representation. So we are strong inducting on n. So we know that P of 1 is true, P of 2 is true, and so on till P of n minus 1 is true. And we want to show that P of n is true, is also true. So now what I'll do is I'll consider the d such that 2 to the power of d is at most n, which is less than 2 to the power of d plus 1. So it is the largest power of 2, which is less than or equal to n, basically. Actually, here I'll assume p of 0 for reasons which will become clear. And yeah, so the base case I'll be taking is just n equals 0. You take no powers of 2, right? Or if you're worried, you can also take n equals 1, where you pick 2 to the power of 0. Okay. So this is the, you're picking the empty set here, basically. So yeah. So the point of this is, since you're removing the largest power of 2, we can consider the number n minus 2 to the power of d. Now this one is obviously less than n. So it'll have a representation, with sums of powers of 2. Right. So I can write n minus 2 to the power of d as 2 to the a1 plus 2 to the a2, and for some even a2. So the idea here is that since I know it is this inequality is true, I know that, okay, I'll write it here. I know that n minus 2 to the power of d is strictly less than 2 to the power of d. So this value I know is less than 2 to the power of d. So that means whatever power of 2 I take, that will be strictly less than d. So is this clear? Like why each term should be less than d?
Yeah, that is clear.
Yeah. So since you have this, what I can do is I can just add this thing here, 2 to the d plus. And this is a valid representation because d doesn't interfere with anything else. So like there's no carryover or anything. And because ai is strictly less than d, so nothing adds up. And so n is a sum of some powers of 2. And to show it's unique, you basically do the same thing, like for, okay, 1 second. So the representation of n minus 2 to the power of d is also unique. And for each n satisfying this, right, it must have 2 to the power of d term. Okay, that's what I said. So the claim is that if this is true, right, then in the representation, okay, representation, it must have, my handwriting is getting worse, but yeah. So it must have 2 to the power of d, because other way, okay, so it clearly can't have 2 to the power of d plus 1 or anything above it, right? So whatever representation it is, it must be stuff with at less than d. So like this, where ai is less than d. So this thing, the maximum value it can have is 2 to the d minus 1, d minus 2, and so on till 1. But then we know this is 2 to the power of d minus 1. But then we already know that n is at least 2 to the power of d. So this is a contradiction. So in the representation of n, there must be 2 to the power of d. And since representation of n minus 2 to the power of d is unique, representation of n becomes unique too, because it is the only possible way to reach n.
Okay.
Right. Okay, so since I don't have that much time right now, I'll just give a briefing about. So basically, induction you can also do in a weird way. So for the proof of AMGM, which states that if you have some positive numbers, this is true. Right. So I won't be giving the proof right now, but you can find it on Wikipedia or like pretty much everywhere. So basically what the Cauchy proof is that you show that if n is true, then so is n minus 1. Right. This obviously doesn't finish immediately because you pick some n and then you show for all values less than it. But what about the values more than it? So what you have to do is you have to get arbitrarily large values. So like 100, everything below it is true. 1000, everything below it is true, and so on. So what you can show is that if n is true, then 2n is also true. And so this is also an induction, right? So using that, you can show that 2 to the power of k is true for all k, right? And since you can go back, right, like root power of k is true, root power of k minus 1, and so on till 1. You can show that every number, it's true for every single number. And so you can, there are weird types of induction you can do too, but strong induction and normal induction are the most common ones. Okay, so I guess I'll just, talk about this. So remember, like the find all thing I said in the beginning, like there are often problems disguised as two problems. So you will need to show two parts. So whenever I say find all, x satisfying p, right? So what I need to show is that I need to find a set S such that if x is in S, right, then x satisfies p. And I also need to show, because otherwise you can say stuff like, okay, x minus 1 equals 0 implies x is 1 or 2, right? This implication is true, but this must satisfy this equation. Otherwise, it's not a solution to it. And if x satisfies p, then x must be in this, because otherwise there is some, like we want to find all such terms. So we need both of these to be true. So in your proof, you'll have to usually write both of them as separate parts. So, okay, as a simple example, find all n such that, okay, so I'll give you n is a positive integer, right? Find all k such that if I have k things in n boxes, then there is a box with at least two things. Right. So for this again, you need to, okay, so like by pigeonhole principle, it should be fairly clear that the set S we are looking for is n plus 1, n plus 2, and so on. So, but this is not enough. You can't just say that since pigeonhole principle is true, S is this. You also need to give examples why, 1, 2, n does not work. Why these things are not in S. You have to show that. So to show that is pretty simple. You just take n boxes and put one thing in each. And since like it's at most n things, right? Each thing will have only one box and there'll be something remaining, or unless it's n, there'll be nothing remaining. But each thing will have at most one box. So that means that these things are not in S because it does not satisfy this. Right. So usually we, we say there are two parts. There's this construction part or obstruction or like destruction, you can also call it. So this is the part where you show that what n work. So for example, the construction here would be for this set. So you showed that for k equals n plus 1, this condition is satisfied. And the obstruction would be, for what s this does not work, for what k this does not work. So yeah, see, it is, quite common to forget one of these parts while writing up, and then you can lose partials on it. So you have to be careful and write both parts. So yeah. And it's obviously like important to verify, the proof too. And the same thing applies for, let's say, finding the minimal or maximal value of something. So let's say I want to find the maximum value of some function f. Okay, yeah. So let's say I want to find minimum value of some function f. Let's say x square, right? For x and reals. Can anyone tell me what this is? Like the minimum value of x square. Okay, it's just like 0 because x square is always non-negative. So the minimum value would be 0. But this is not enough because you could also automatically say that x square is at least -1. But the reason this is not a minimum is because there is no x satisfying x square equals -1. So there is nothing reaching the equality case here. So that's why this is not the minimum. But this is the minimum because, for x equals 0, this does have a x square equal to 0. And so equality case is achieved. So as an example, if you're doing a problem like a plus b plus c is equal to 0 and maximize ab plus bc plus c, right? So in this case, okay, most people would be able to get the bound pretty easily. They'd be like, okay, whole square is 0. Right, and then since this is positive, this entire thing, you get you get AB plus BC plus C is at most 0. But you have not shown that this is the maximum value. You also have to find such A, B, and C such that AB plus BC plus CA is indeed equal to 0. So in this case, it's pretty easy to see because setting all of A, B, and C to be equal to 0 satisfies A plus B plus C equals 0 and AB plus BC plus C equals 0. So yeah, checking the equality case is also important when writing proofs. So again, if you didn't write this, you might lose a mark or something. So yeah. Yeah, I think this is it. If you want an exercise on induction, you could like Yeah, so instead of base 2, you could try showing it for base 10 and showing uniqueness to it. And you could look up sources like mathematical circles or problem solving strategies for more problems on this. So yeah, that's it. Thanks for attending the class.
I'll stop recording or it. Okay.
Yeah.